Hello everybody, and welcome to Section 5.3, Integration by Substitution. We are looking at page 114 in the workbook, and this is the very last section in our calculus course. So we have made it to the end of the rainbow here. And Section 5.3 is sort of a continuation of the work that we started back in Section 4.4 when we talked about antiderivatives. We made a list of antiderivatives of some common functions, and we're going to see that the substitution rule gives us a way of finding antiderivatives for a lot more functions. Okay, so we're going to see, as we sort of unpack this together, that the substitution rule has a very strong connection to the chain rule. So before we dive in and formally state the substitution rule, we're going to do a couple of preliminary examples here just to explore that connection. So let's start with example 1 together here. They give us a problem from much earlier in the course just to take a derivative using the chain rule. All right, so our function is f of x equals sine of x cubed. Let's see if we can calculate its derivative together. Okay, so using the chain rule, we would notice that we've got an inside function of x cubed. So taking the derivative of this would be taking the derivative of sine of u and getting cosine of u. And then there's that second step of multiplying by the derivative of the u. So we get cosine of x cubed times the derivative of x cubed. That's going to give us cosine of x cubed times 3x squared. There's our answer. Okay, but what's interesting is we can take that equation and turn it around. Okay, so we took the derivative and got this function, so we could also say that the antiderivative of cosine of x cubed times 3x squared is equal to sine of x cubed. And that's what part B is getting at. If we take the antiderivative, remember that's what this integral sign is representing, antiderivative of cosine cubed times 3x squared, we should get back to the function that we started with. Okay, that's just restating what we calculated in part A in terms of antiderivatives. Okay, kind of all of the examples that we're going to do have that sort of flavor to them. So let's move on and look at example 2 here. So this time they'd like us to take the derivative of e to the 3x using the chain rule. Okay, so this time our u is 3x, so we'd ask ourselves, how do we take the derivative of e to the u? Well, it's going to stay the same, multiplied by the derivative of that u. And this takes us down to e to the 3x times derivative of 3x is just 3. We could rewrite that as 3e to the 3x if we wanted to. Okay, and again, we can turn that statement around. If we take the antiderivative of 3e to the 3x, it should get us back to e to the 3x. Okay, filling that into part B, that would be saying that the indefinite integral of 3e to the 3x is e to the 3x plus c. Okay, and at this point, I would like you to maybe pause the video, see if you can do examples 3 and 4 on your own, okay, and after you've made an attempt at those, you can start the video up and compare your answers. Okay, welcome back. So hopefully you gave examples 3 and 4 a try. Let's work through those and see if we got the same answer. So 3a asks us for the derivative of e to the negative x squared. Let's take that derivative here. So derivative of e to the u is just e to the u again times the derivative of the u. So the derivative of the negative x squared is negative 2x, which if we wanted to, we could rewrite like this, negative 2x times e to the negative x squared. Okay, and turning that statement around, we could say that the antiderivative of negative 2x e to the negative x squared is the function that we started with, okay, which would look like this. The indefinite integral of negative 2x e to the negative x squared is e to the negative x squared plus c. Okay, and finally, we come to example 4 here. Okay, one more time. So this time they're starting us with the function f of x equals cosine of 5x. If we take that derivative, we're taking the derivative of cosine of u, which is negative sine of u, times the derivative of u, and the derivative of 5x is just 5. Okay, if we rewrite that, okay, that's negative 5 sine of 5x. Okay, what's interesting about this one is they've got two blanks that they'd like us to fill in here. Okay, so the first one is just the same thing that you did in examples 1 through 3, reversing this and saying that if this is our derivative, then the antiderivative of negative 5 sine of 5x should get us back to cosine of 5x. Okay, which is what this is saying. Okay, what if, though, we wanted an antiderivative for the function sine of 5x? Okay, notice that that's similar to the left-hand side of this equation, except that the negative 5 isn't there. So you might, one way to think of this is to ask, what's the connection between this first formula and this second formula? What we could do to get from one to the other is just divide both sides by negative 5. Okay, that'll make the left-hand side here look like the left-hand side here. And so what that should mean then is we can divide the right-hand side also by negative 5, and so we might expect that we'd get negative a fifth cosine of 5x. We just took the cosine of 5x that we had over there and divided it by negative 5 as well. Okay, and we'll see that that really does work. We can get away with dividing by constants like that. We did a little bit of that actually already in section 4.4. Okay, and as we go forward in this section, we will formally state the substitution rule and use it to calculate integrals.